duals. And this is based on a work in progress, so it's not finished yet, but I think that it's worthwhile to share something. And we start with well, I didn't prepare any slide for you, Daniel, sorry.
I
wish I had a giant panel. I would pay more for that. So here, so the problem has to deal with the weird things that happens in geometry of curves in positive characteristics. Okay, so we consider an algebraic equals to K and a projective space of dimension n. By a curve, I always mean projective, irreducible, non-degenerate, algebraic. Non-degenerate means that it is not on a hyperplane of Pn. Okay. So, as I said, we can expect weird things happening in positive characteristics. Let me give some examples. For instance, if you consider the sequence of integers that are realized as intersection multiplicities of your curve with hyperplanes at the general point, then when the characteristic of the field is zero, what's the point?
A bolinha vermelha do meio.
Vermelha? Ah, aqui. Não é uma bolinha. It's not. Thank you. Thank you. Then when the characteristic is zero, then the sequence is this classical sequence, 0, 1, etc. to n. Okay. However, this not necessarily hold in positive characteristics. As a matter of fact, and when the curve, well, I will introduce that later, but this curves that have this sequence are called classical curves. Okay. So in positive characteristic, we may have non-classical curves. Okay. Another example is if you consider a dual projective space with this space, the points of this space corresponds to hyperplanes in Pn. Okay. So to each hyperplane, you have a point, corresponding point in what we call the dual projective space. And given a curve in Pn, you can construct the dual curve using the osculating hyperplanes. Okay, so you take a smooth point of your curve, and it has only one osculating hyperplane, which is the hyperplane with the highest possible intersection multiplicity. And this hyperplane will correspond to a point, and you take the closure of all these points in Pn prime, and you have the dual curve. Okay. And the cover that sends points of x to the dual curve, actually you can extend this process to a morphism, and this is called the strict Gauss map. In this talk I will say only Gauss map. Okay, I will drop this word strict, but so in this talk Gauss map sends points to hyperplanes. Okay, osculating hyperplanes. Sorry. And when the characteristic of the ground field is zero, then you have this bidual phenomenon. Okay, so the dual of the dual is again your original curve. Okay, more than this, you have that when you take the composition of the Gauss map of your curve and the Gauss map of the dual, then this is an identity map. Okay, it fixes all the points. And in particular, in this case, the dual curve is non-degenerate. Okay, it's not on a hyperplane of Pn prime. And this situation sometimes doesn't happen in positive characteristics. Okay, when your curve is classical, then it's the same. It's pretty much the same. But when the sequence is non-classical, it's not this one. Then both separable and inseparable degrees of gamma of the Gauss map can be positive. Okay, and so Okay, but why do we care about dual curves anyway? First of all, it's too much fun. It's nice to play with these weird objects. So, but essentially, we want to know for which curves we can use the dual incidence results. Okay, so when you have an incidence result in geometry, it's nice to have when the curve has well-behaved duality, which is this. So every time you have an incidence result, you actually have two results. Okay. The most simple example I know is this one. Okay. So you take a line defined over FQ, it has Q plus 1 FQ points. So using duality, through a FQ rational point, you have Q plus 1 lines. Okay. Only using this correspondence. And it's interesting to know when this type of results hold. Okay. So that's why I'm studying this. In particular, I study this for double Frobenius non-classical curves. I will get there, give this definition. First, some preliminary results. This was just an introduction, the preliminary start now. So you have a curve, a space curve with this order sequence, which is all the possible numbers realized as intersection multiplicities of planes with that general point or at the general point of the curve. And we'll say that your curve is classical when this sequence is the classical sequence. Otherwise, we'll say that the curve is non-classical. Okay. And so, as I said before, given a smooth point of your curve X, there exists a unique hyperplane intersecting your curve at this point with the highest possible multiplicity. Okay, and this hyperplane, in this case, a plane. Okay, I forgot to repeat. And this plane is the osculating plane at P. Okay. So in this talk, every time I say that your curve is FQ Frobenius non-classical, I mean that at the general P in X, the image of the Frobenius map lies on the osculating plane at this point. Okay, why I put this in red? Because this is not the quite definition of Frobenius non-classical curves. It's the same thing for plane curves, but in higher dimensional space is not. This condition implies Frobenius non-classicality, but I will use this property here. Okay, if I have time, I can explain why this is. I will say that these are the interesting Frobenius non-classical curves. Okay, I can explain later if I have time. If you want to ask me later when any questions, I can explain. Okay. Okay. So, and in this talk, well, let's define that a curve in Pn is said to be strange when all the tangent lines at general points are concurrent. Okay, they meet the same point. And in this talk, I will assume that my curves are not strange. Okay. Okay. So let's get to the double Frobenius non-classicality. This is a very well-known object. Okay. If you have a plane curve, so you take two coprime numbers, u and m. Assume that m is bigger than 2. And if you have a plane curve that is fq to the u and fq to the m Frobenius non-classical at the same time, then your curve must be this one. Okay. I will call, in this talk, I will call this the Borges curve because it was introduced by Heriberto Borges. Many properties of this curve are known. Genus, number of rational points, singularities. Recently, by a paper in a paper by Heriberto, Pietro Speziali, and Professor Gabor Korczmarz, they show that this have large number of linear automorphisms, I guess, right? As large as can be, actually, right? And so everything is known. not everything, but many things are known about this curve, okay? But this is for plane curves, okay? When you are in higher dimensional spaces, you don't have a unique double Frobenius non-classical curve. I mean, you can have infinitely many non-isomorphic double Frobenius non-classical curves. However, I would like to understand what happens if I put the extra condition on the dual. I mean, if you have a curve that is double Frobenius non-classical, space curve, double Frobenius non-classical with degenerate dual, such that the dual is actually a plane curve, okay? So in this case, we don't have a classification, but you can track your curve in this object, okay? So assume that you have a space curve with this sequence, or the sequence, and take two numbers, for prime numbers, with m, u and m, with m bigger than 2. Then these conditions are equivalent. Your curve is double Frobenius non-classical, such that the stick duals degenerate, and your curve lies on a cone over the Borges curve. Okay, so you don't have a classification, but you know that your curve. So if you have your Borges curve here, so your curve must lie somewhere here, okay? Something like that. So again, it's not unique, but you know where it must live, okay? And which is interesting because it has to do with the only double Frobenius non-classical plane curve. So, and with this on hand, we can give a criteria to conclude when double Frobenius non-classical space curves have degenerate duals. So if you have a double Frobenius non-classical space curve, I forgot to say that, it's right, I write it down, but in this case, this number, epsilon 3, actually equals q to the u, okay, this u, right? So, okay. So you take a double Frobenius non-classical curve, space curve, and if this number is not q to the u, then you know that your curve is non-degenerate, so you can try to use a couple of incidence results to produce the dual versions of it, okay? And what more can we say? Another interesting thing is the following. So again, you have a double Frobenius non-classical curve, m bigger than 2, u and m for prime numbers, and if the dual is degenerate, then the degree of this projection here, the degree of the projection coincides with the separable degree of the Gauss map of X. Okay. In particular, when your Gauss map is purely separable, then you know that then you have a sort of a classification. Then it must be irrationally equivalent to the Borges curve. So it's a model in P3 of the Borges curve. Okay. So all of this happens when m is bigger than 2. What happens if m equals 2? Well, in this case, we can show that actually the dual, if you have double Frobenius non-classical and FQ and FQ squared Frobenius non-classical curve with 3, then the dual must be non-degenerate. Okay. Okay. Oh, we're very fast. Actually, the end of the talk. Lunchtime, right? Let's go. Okay, so now we define the group of linear automorphisms of a curve. Okay, so which is the automorphisms that can be represented by matrices. Okay, so I will call this group out L of X. Okay, and inside this group we consider this subgroup H. Composed by all the linear automorphisms that preserves genetic fiber of the Gauss map of your curve. Okay, So you have a Gauss map, you have a pre-image, the fiber, and you consider the linear automorphisms that preserve this as a set. Okay, not fixing point-wise, but preserves as a set. Okay, and H we have the following. We have the structure of this loop. It's a semi-direct product of an elementary abelian group and a cyclic group, such that the order of this cyclic group divides the order of the elementary abelian minus 1. People that are familiar with automorphisms might suspect where this comes from. And H is actually a normal subgroup of the linear automorphisms, and the factor group is a subgroup of the linear automorphisms of the dual curve. Okay, you may think, okay, this guy's cheating. I saw that before. This is Galois theory, right? But as a matter of fact, it's not, because in this usually when this is non-trivial, usually not usually, always. When this is non-trivial, then the dual is degenerate. And when the dual is degenerate, the Gauss map is not separable. So this is not a Galois cover. The Gauss map is not a Galois cover in this case. Okay? So these are not Galois groups. And that's why I put this here. I found it interesting. Okay? And okay. But what can we say? How we connect this to the previous slides? So, okay, consider space curve over FQ with this order sequence. Here, as always, assume that P is given at 3. And if your curve is double-Frobenius non-classical, but with the same parameters as before, and H, that subgroup H is non-trivial, and the order is not divisible by P, then your curve must be FQ irrational equivalent to this one. This is the polynomial, the first one, defining the Borges curve, and you have z to the n equals a rational function here, the function field of the Borges curve. Okay, so roughly speaking, it's a Kummer extension of the Borges curve. And moreover, we already know that epsilon3 equals q to the u, sorry. And if we call V this function, the projection of this rational function on the function field of the Borges curve, then epsilon2 is bigger than 2 if and only if this V is a solution of this differential equation. Okay? And well, that's it.
Next question, comment?
Maybe we have time to explain. It's additional.
You really want that? Okay. My God. So, actually, what Cesar is asking is why the interesting definition of Frobenius non-classical curve is this one. Thank you for your question, Cesar. And okay, I can. You have a curve tree. Assume that it's given by these coordinate functions, 1, x, y, affine coordinate functions. So your curve will be Frobenius non-classical, FQ Frobenius non-classical if this guy so let's assume that x is separating, okay? This was sorry. These are the Hasse derivatives, okay? So the curve is called FQ Frobenius non-classical if this is vanishing on the function field, on the curve of the function field. Okay. Otherwise, well, in this case, it is Frobenius non-classical. But as a matter of fact, when your curve is Frobenius non-classical, anyway, non-classical, sorry. Planar curve is defined over FQ. We have a FQ Frobenius order sequence associated. Okay. And these numbers are the smaller numbers in the lexicographical order that for which when you plug here, the D0, D1, DE1, DE2, this is non-vanishing. Okay, so it is not. This sequence is not the sequence 0, 1, and 2. Okay, and what happens is that this is always a subsequence of the order sequence. Okay, so this property implies that the last number of your sequence, the need to actually equals epsilon 3. But why this type of Frobenius non-classical is interesting, at least for me, because if we don't have that, if epsilon 2 is actually bigger than 2, then this sequence will always be non-classical. Okay, so it's kind of artificial Frobenius non-classical. It will be Frobenius non-classical for all extensions of Q. Okay, by the definition. But we want to emulate what happens in the plane curve case. Okay, the Frobenius map sending to. That's why. I hope you're satisfied with my answer.
Any other question, comments?
I enjoy the opportunity to park, but the rest is also very But just to say that this kind of I think that as a consequence of your results, you may also be able to classify 3 faults before with many points, because there is some recent work by that and others which basically tells that you have some kind of you want to have 3 many points. In most of the cases, it happens that if you take the upper, you take the osculating hyperplane, you make the intersection, it's a cone over an x. So, yeah, I think it's.
Thank you.
There are some very nice.
Thank you. Please send me that later. Thank you.
Any other question? Comment? We come back at 2 p.m.